There's a particular kind of knowledge that doesn't feel like knowledge. It feels like furniture. You don't remember acquiring it. It's just there, occupying space, holding other things up. And you've never once thought to look at what it's sitting on. Gravity is like that for most people. You learned it the way you learned to breathe through your mouth when your nose was blocked. Not from a lesson, not from anyone sitting you down and explaining the mechanism, but from the steady, patient pressure of the world doing what it does and your body eventually catching on. A cup rolls off a counter. You watch it fall. Something in you absorbs the direction of that fall and files it away without commentary. Rain goes down, smoke goes up, you go down if you jump and you come back down if you're thrown. And there's an order to all of it that arrives so early it doesn't feel like information anymore. It feels like gravity itself. The room you're in right now, whatever room that is pulling you toward its floor. You probably haven't thought about that sentence in those terms. The chair beneath you, the mattress, the couch, whatever's holding you at this particular hour, it's not really holding you so much as it's interrupting a fall that would otherwise continue indefinitely downward. You're not resting. You're being stopped. That's a strange way to think about lying still. And yet that's the mechanical truth of it. You are, in this moment, being pressed against a surface by a force that does not stop, does not pause, does not take any interest in whether you're awake or asleep or paying attention. It is just there, underneath the night, pulling at the same stubborn, wordless rate it always has. Most nights you don't notice a all. Tonight you might, just briefly, because someone said the word. Isaac Newton didn't discover gravity. That part is sometimes forgotten. What he did, and it was extraordinary, it was genuinely strange for its time, was describe it. He put a number to it. He said, "Here is a relationship between two masses. Here is a distance. Here is what you can calculate." And the calculation worked. It worked for the moon, it worked for the tides, it worked for the orbit of every planet anyone bothered to check. For 2 centuries the calculation worked so reliably that questioning it would have felt a bit like questioning arithmetic. So nobody did. Not really. Not with any sustained seriousness. The rule settled in the way useful rules do, by being correct enough, consistently enough, that the edges of it went uninspected. Gravity pulls on things with mass. The more mass, the harder the pull. The farther away, the weaker it gets. That's the version most people carry. That's the version that feels like furniture. But here's the thing, and this is the question that starts this whole particular night. Light has no mass, not a small amount of mass. Not mass that's technically there but negligible. No rest mass at all, which is the physicist's way of saying if you could somehow stop a photon and put it on a scale, the scale would read nothing. The photon is, in the strictest sense, massless. So under Newton's rule, the one that settled so quietly and so early, gravity should have nothing to grab. There's no mass in the equation. The force should be zero. Light should sail past a star or a planet or a galaxy without the slightest nudge, travelling in a straight line from wherever it started to wherever it ends up, completely unaware that anything heavy is nearby. Except it doesn't. Light bends. We've watched it bend. We've built instruments specifically to measure how much it bends, and we've confirmed the measurements dozens of times since with radio telescopes and satellites, and now the kind of deep field images that look almost too geometric to be natural. These perfect, impossible rings of light curving around objects they were never supposed to touch. The rule was wrong. Or, not wrong exactly. Not wrong in the places people were looking. More like incomplete in a way that nobody noticed until something showed up that the rule couldn't account for. There's a version of this realization that's dramatic. A paradigm overturned. The genius who saw what everyone else had missed. And some of that narrative is true, in the broad strokes. But the quieter version is more interesting to me. if I'm being honest. The quieter version is about how long the incomplete rule sat there, comfortable and unexamined, doing its job well enough that nobody thought to press on it. How many people looked at the night sky during those 2 centuries and didn't ask the question, not because they couldn't have, but because the furniture was in the way? We're all doing this about something. That's not a judgment. It's just a structural feature of having a mind that has to organize more information than it can consciously hold at once. You build a framework. The framework works. You stop checking the framework. Gravity pulls on mass. Rain goes down. The cup hits the floor and breaks in the same direction every time. If this kind of slow late-night thinking about the universe is something you want to keep coming back to, this project exists entirely because people choose to support it directly on Patreon. There's no algorithm funding this, no studio, no department budget. Just a self-funded effort to make space for physics that doesn't rush. If you'd like to help keep it going, you'll find the link in the description. What Newton gave us was a ledger. 2 columns, mass here, mass there. Distance in the denominator, force as the result. A clean accounting system for a universe that, it turns out, doesn't entirely organize itself by that logic, but does so closely enough that the discrepancy stayed hidden for a very long time. The discrepancy is massless light, bending. And the explanation, when it finally came, and it did come slowly and with considerable difficulty, didn't just fix the equation. It replaced the idea of what gravity is. Not a force that reaches between masses like a stretched rubber band. Something else, as something that's harder to picture and harder to say, and has to do with the shape of the thing that everything, light included, moves through. That shape is where this is heading, but not yet, not tonight, not yet. For now, just the rule. The familiar, comfortable, slightly wrong rule that sat in the furniture of the mind for 200 years before anyone found the crack in it. You've been living with gravity your whole life. You felt it in floors and mattresses and the tug at the bottom of a staircase. You've never once had to think about it, and it has never once let you go. And the thing it bends that it shouldn't be able to bend, that's where the real question starts. Not with the bending, with why the rule said it couldn't. There is a particular kind of person who asks a question that nobody asked before, and then gets almost entirely forgotten for it. Not forgotten in the angry sense, not erased or buried by someone with a reason to bury things, just overlooked in the slow structural way that happens when a mind arrives at a doorway slightly too early, before the corridor behind it has been built, before anyone has reason to walk that way. The question gets filed, the answer gets filed, and the world keeps moving at its own pace, which is rarely the pace of the person doing the asking. Johann Georg von Soldner was a German mathematician and astronomer, working in Berlin in the opening years of the 19th century. He wasn't obscure by the standards of his time. He held serious positions, published real work, contributed to practical astronomy in ways that mattered. But the thing he did in 1801, the thing that concerns us now, sat in a journal for over a century before anyone picked it up with the kind of attention it deserved. And even then, it was mostly picked up to show what it got wrong, which is a slightly unfair way to treat a calculation that got almost everything right. What Soldner asked was simple enough to state in a sentence. Does light fall? He was working inside Newton's framework, the same one from the previous chapter, the ledger, the 2 columns of mass and distance, and Newton's framework had this interesting quality of being very complete feeling without quite closing off every question. Newton himself had wondered in print in the first of his optics queries published in 1704, whether bodies act upon light at a distance. He didn't calculate it. He raised it the way you raise something when you're not sure it belongs in the room yet. Carefully, briefly, with a kind of academic throat clearing that doesn't commit. Soldner committed. He treated light as if it were a stream of tiny particles, corpuscles, in the language of the day, travelling at a known speed, and he asked, if these particles have some effective mass, however small, what would Newton's gravitational formula predict about their path near a massive object like the Sun? He worked through the geometry. He accounted for the velocity, the distance, the mass of the Sun, the angle of closest approach. He produced a number. The number was 0.84 arcseconds. An arcsecond is 1/3600th of a degree. It is, practically speaking, a very small angle, the kind of displacement that is almost invisible to the naked eye and only barely detectable even with the instruments of 1801. Soldner knew this. He noted in his paper that the deflection would be so small as to probably lie beneath the threshold of practical observation, and that it might therefore be of more theoretical than experimental interest. He was right about the size. He was right about the difficulty. He was wrong, it turned out, about the number, but not in the way you might expect. The number wasn't an overestimate or a product of sloppy reasoning. It was derived correctly from the assumptions he was working with. The problem was the assumptions, specifically, one assumption, an assumption so embedded in the Newtonian framework that Soldner had no way of knowing it was an assumption at all. The assumption was this, that space is flat. Not flat in the everyday sense, not flat like a table, flat in the geometric sense, that the shortest distance between 2 points is always a straight line, that parallel lines never meet, that the presence of a massive object might exert a force on things nearby, but doesn't change the underlying structure of the space those things move through. Space in Newton's picture is the stage. It is not an actor. It sits there, fixed and Euclidean, while mass and force and motion perform on it. Soldner had no reason to doubt the stage. Nobody in 1801 had any reason to doubt the stage. The stage had been reliable. The stage had held. And so when Soldner calculated the path of light near the Sun, he calculated a deviation caused only by the gravitational tug, the pull on the particle in the Newtonian sense, without accounting for any curvature in the geometry itself. What he got was half the answer. Specifically, almost exactly half. The value that general relativity would eventually produce and confirm is 1.75 arcseconds. Soldner got 0.84. The doubling, when it came 114 years later, wasn't the result of finding a new force or correcting a math error. It came from realizing that the stage itself was bent. I find something almost uncomfortable in that gap. Not tragic, that's too strong, but uncomfortable in a quiet, specific way. The gap between 0.84 and 1.75 is not a rounding difference. It is a structural one. It represents an entire layer of reality that Soldner's framework didn't include, not because he failed to look for it, but because the concept didn't yet exist in any form he could have accessed. He was using the best available tools. The tools were good. The tools produced a result that was coherent, internally consistent, and wrong by a factor that has a precise physical meaning. That's not an embarrassing situation. That's actually what physics looks like from the inside, a lot of the time. Coherent, consistent, and containing a gap that won't become visible until someone builds the thing that reveals it. Einstein, working in 1911, made essentially the same calculation as Soldner. He didn't know about Soldner's paper. It had been mentioned in passing in a few places, but not in ways that reached him. He derived the same deflection value, 0.83 arcseconds, using the equivalence principle as his starting point rather than Newtonian corpuscular mechanics, and he arrived at roughly the same place by a different road. He published it. He thought it was right. And then, and this is the part worth pausing on, He kept working. The full theory of general relativity took 4 more years. When it arrived in 1915, Einstein revisited the light-bending calculation and found that his 1911 value was also half of the correct answer. The equivalence principle alone, which was already a radical departure from Newton's thinking, gave you 1 layer of the bending. The spatial curvature of space-time, the geometry of the stage now no longer fixed, gave you the other. He corrected himself, publicly, with apparent calm, the way someone corrects a sentence they've already said aloud when they realize mid-air that it came out wrong. The correct value, 1.75 arc-seconds at the limb of the Sun. Soldner's paper was rediscovered in 1921, mostly by people who wanted to use it to argue that Einstein hadn't done anything original, that light bending near the Sun was already a Newtonian prediction and didn't require a new theory at all. This argument doesn't hold up, and it didn't hold up then. The Newtonian prediction is half the observed value. Einstein's prediction matches it. That isn't a technicality. The difference between 0.84 and 1.75 arc-seconds is the difference between gravity as a force acting on things and gravity as a curvature in the fabric through which everything moves. One of those is a description of something pulling. The other is a description of the shape of space itself. Soldner got the pulling part. He got it correctly from within a framework that had no way of knowing about the shape. There's a hum in this kind of history that doesn't resolve into a lesson cleanly. The Berlin Observatory in 1801 would have smelled of lamp oil and old paper and probably something metallic from the instruments, that specific cold smell that brass gets in the winter. Soldner would have worked by the kind of light that required you to lean close to the page. He asked a good question. He answered it as well as anyone could have. He published, he moved on, and the paper sat. 114 years is a long time for a number to wait. The question he asked, does light fall, turned out to be the right question. The framework he used to answer it turned out to be the wrong framework, or not wrong exactly, but 1 layer short of the full geometry. And the layer that was missing, the thing that doubles the deflection, the thing that brings the answer from Soldner's number to Einstein's, that's the layer this whole night is quietly building toward. Not yet, but soon. The stage, it turns out, is not flat. And once you know that, nothing about the bending of light is simple anymore. You are falling right now, not metaphorically, not in the poetic sense where falling means something about emotional states or the passage of time, in the plain mechanical sense, the sense that would show up in an equation, you're in free fall and the floor is stopping you. That distinction matters. It matters in a way that took a long time to fully articulate. And once it was articulated, it changed what gravity meant at a fundamental level. Not adjusted it. Changed it. Feel the surface beneath you for a moment. Whatever it is, mattress, cushion, floor, the specific give of whatever you're lying on at this particular hour, there's a pressure there, a persistent, dull push against your back or your side or the soles of your feet depending on how you're arranged. That pressure is real. You can feel it without thinking about it, the way you feel the temperature of a room without deciding to. Now here is the strange part. That pressure is not gravity. Gravity is not what you feel when you're sitting still. Gravity is what you'd feel, or rather what you'd stop feeling if the floor disappeared. The pressure you feel right now is the floor pushing back against a fall that hasn't been allowed to happen. You're being held out of free fall by the solid resistance of whatever surface is between you and the ground. Free fall, the actual experience of gravity without obstruction, feels like nothing. It feels like floating. Astronauts in orbit aren't beyond gravity's reach. The Earth's gravitational pull at the altitude of the International Space Station is still roughly 90% of what it is here. They feel weightless because they're falling continuously. The station is falling too, in a long curved path that keeps missing the Earth because of how fast they're moving sideways. Everything falling together at the same rate feels, from inside, identical to floating in empty space. Weight is not gravity. Weight is the interruption of gravity. This took me a while to actually sit with. Not the sentence. The sentence is easy enough. The sitting with it part is harder, because everything in ordinary experience points the other direction. You feel heavy when the elevator accelerates upward. You feel your stomach lift when it drops. The body has a very clear, very persistent sense of which way is down, and that sense feels like gravity, feels like it's tracking something real and external, and it is tracking something real, just not exactly what it seems to be tracking. What it's tracking is the force on your body, the net push, the thing stopping you from falling. When the elevator accelerates up, the floor pushes harder. When it drops fast, the floor pushes less. Your body reads these forces and calls them gravity because in ordinary life the two are always paired. Gravity is always there, and the floor is always resisting it, and the feeling of weight is what that resistance produces. Remove the floor and the feeling vanishes, even though gravity hasn't changed at all. There's a specific smell in gymnastics facilities. Chalk dust and old foam mat, slightly stale in the way closed rooms get when a lot of bodies have been in them. I thought about this once, watching someone on a trampoline at the peak of a jump. For just that fraction of a second at the top before the downward motion begins again, there's a stillness. A brief interruption of the floor's resistance, a brief return to what fall actually feels like from the inside. Nothing. That's the honest answer. Free fall feels like nothing in particular. Now, light. A photon leaves a star. It travels. It encounters the gravitational field of a galaxy, or a cluster of galaxies, or a single massive star sitting between it and wherever it's going, and it bends. Under Newton's picture, this required some uncomfortable assumptions. If gravity pulls on mass, and light has no mass, then there's nothing to pull. Soldner got around this by treating photons as if they had some tiny effective mass, a convenient fiction that produced a number, and a number that was, we now know, half right. But it was always a slightly awkward manoeuvre. You had to pretend light was something it isn't in order to get gravity to touch it at all. General relativity doesn't need the fiction. In the picture Einstein eventually completed, there is no force reaching out to grab the photon. There is no pull. What there is instead is a geometry, a shape to space-time itself, and the photon does what every free-falling object does. It follows the geometry. It travels the straightest path available to it in the space it's moving through. And if that space is curved by the presence of mass, then the straightest available path is itself a curve. The photon isn't being deflected. The space it's moving through has a different shape than flat space, and the photon is following that shape as faithfully as anything can. This is where the analogy to falling becomes something more than illustrative. You, right now, being held against a surface by the floor, you're not in the natural state. The natural state, under general relativity, is free fall. Free fall is the absence of force, not the presence of it. The astronaut in orbit is closer to the natural unforced state of motion than you are, lying completely still, and the photon, massless, never resting, moving at the only speed it knows how to move, is in permanent free fall. Always. There is no floor to stop it, no surface pushing back, no interruption. It falls through the geometry of space-time continuously, from the moment it's emitted to the moment it's absorbed, and it follows that geometry the way water follows a surface it's poured onto. Not because something is pulling it, because that's what free-falling objects do. They go where the geometry goes. The bending of light near a massive object is, in this sense, the same phenomenon as an orbit. A planet orbits a star not because the star is reaching out and holding it with some invisible tether, but because the planet is in free fall through a curved geometry, and the curve keeps bringing it back around. The photon near a galaxy is doing the same thing, just at a speed that doesn't allow it to orbit in the traditional sense. It passes through, deflected, continuing on. Both are falling. Both are following the shape of where they are. The photon just doesn't have the option of slowing down, so when the question comes, why does gravity bend light that has no mass? The answer, at least the beginning of the answer, is that the framing of the question contains the old assumption. It asks why gravity reaches out and grabs something it shouldn't be able to grab, but gravity, properly understood, doesn't grab anything. It shapes the space that things move through. And things that move through shaped space follow the shape. Light follows the shape. It has always followed the shape. We just needed a framework that could see the shape to understand why. That framework, where it came from, what it actually says, and why it took the specific form it did, is what the next few chapters are sitting with. It starts earlier than the equations. It starts with an elevator and a thought that arrived quietly and then didn't leave. Before the equations, before the geometry, the tensors, the formal machinery of a theory that took a decade to complete. Before any of that, there was a thought, a single, stubborn thought that Einstein described years later as the happiest thought of his life, which is a strange thing to say about something that arrived, as far as anyone can tell, while he was sitting at a desk in a patent office in Bern, doing work that had nothing to do with gravity. The thought was this: a person falling freely feels no weight. That's it. That's the whole seed. A person in free fall, genuinely free fall, no air resistance, no surface, nothing interrupting the fall, would have no way of feeling gravity acting on them. Not because gravity had stopped, but because everything around them, every object in their immediate vicinity, would be falling at exactly the same rate. And in that shared falling, there would be no differential, no force pressing body against floor or floor against body, no sensation to report. From inside the fall, it would feel like floating. From inside the fall, it would feel like gravity wasn't there at all. Einstein held that thought and turned it over. The way you turn a smooth stone in your hand when you're thinking about something else. Not examining it exactly, just keeping it in contact with the mind, letting it warm up. What he was sitting with was a question about indistinguishability. If you're in a closed room, a box, an elevator, a sealed container of any kind, with no windows, no instruments connected to the outside world, nothing but the room and your own body and whatever objects are in there with you, there are two situations that would feel identical. The first, the room is sitting on the surface of a planet and gravity is pressing everything downward at the familiar rate. The second, the room is somewhere in empty space, far from any gravitating body, being accelerated upward by a rocket, say, or some other mechanism, at exactly the rate that gravity would have pressed things downward. You could not tell the difference. Drop a ball in the first room, it falls to the floor at a certain rate. Drop a ball in the second room, the accelerating one, out in empty space. It falls to the floor at the same rate, because the floor is rushing up toward it. Stand on a scale in the first room, it reads your weight. Stand on a scale in the second room, it reads the same weight. Every measurement you could make, every experiment you could run, every physical sensation available to your body, they would all return the same result. Gravity, in a small enough region, is indistinguishable from acceleration. Now flip it. The other side of the same coin. If you are in a closed room in free fall, an elevator with a cut cable say, dropping without resistance, everything in the room falls with you at the same rate and you feel nothing. No weight, no downward pull, no sensation of gravity whatsoever. And this experience, this complete absence of gravitational feeling, is identical to what you would experience if the room were floating in empty space, far from any mass, not accelerating, just drifting. Free fall is indistinguishable from the absence of gravity. These two observations together, gravity feels like acceleration, free fall feels like the absence of gravity, form what became known as the equivalence principle. And the equivalence principle is not a small technical claim. It is not a footnote. It is the load-bearing wall of general relativity, the thing the whole structure is built on top of, and in 1907 it arrived in Einstein's mind as a feeling before it arrived as a formula. The patent office in Bern had that particular institutional stillness that large bureaucratic buildings get in the afternoon, the kind where you can hear a clock somewhere but can't quite locate it, where the light through the windows is yellowish and flat and not entirely convincing. I don't know this for certain. I'm assembling it from photographs and the general texture of early 20th century Swiss government offices, which probably smelled faintly of ink and radiator heat, and someone's lunch from 2 hours ago. Einstein was 28. He had already published the special theory of relativity 2 years earlier, a theory that dealt with motion at constant velocity, with the strange things that happen to time and space when you're moving very fast in a straight line. What he hadn't yet touched was the harder problem. What happens when you accelerate? What is the relationship between acceleration and gravity? What does it mean that these two things, in a small enough room with no windows, feel exactly the same? He would spend 8 more years answering that question properly. But the answer started here, in the feeling, the recognition that the sameness wasn't coincidental, that if two things are completely indistinguishable in every physical measurement, they might not just be similar. They might be, in some deeper sense, the same thing. This is where it gets hard to hold without some mental effort, so it's as worth going slowly. If gravity and acceleration are truly equivalent, not approximately, not for practical purposes, but in a deep physical sense, then the effects of gravity should follow from the effects of acceleration. Whatever acceleration does to light, to time, to the geometry of a small region of space, gravity should do the same, because they are the same locally. In a small enough box for a short enough time you cannot separate them. An acceleration does something to light. Imagine a photon entering the side of an accelerating room through a small hole in the wall. The photon travels in a straight line. Light always travels in a straight line through empty space, that much is given. But the room is accelerating upward while the photon is crossing it. By the time the photon reaches the far wall, the room has moved, and the point where the photon hits the far wall is lower than the point where it entered, relative to the room's frame of reference. From inside the room, the light appears to have curved downward. The light didn't curve. The room moved. But from inside the room, with no reference point outside it, the distinction between those two descriptions is, and here is the word that matters, meaningless. If the equivalence principle holds, and if an accelerating room produces an apparent downward curve in a light beam, then a gravitational field should produce the same apparent downward curve in a light beam. Not as a side effect, not incidentally, as a direct consequence of what gravity is. Einstein published this in 1911. He predicted that light would bend near the sun. He gave a number, 0.83 arcseconds, almost exactly Soldner's number, arrived at through completely different reasoning, and he was, as the last chapter noted, half right. The half he was missing wasn't a calculation error, and it wasn't a flaw in the equivalence principle. The equivalence principle is correct. The problem was that the equivalence principle alone, the thought experiment with the elevator and the photon, captures only part of what happens to spacetime near a massive object. It captures what happens to time. Near a massive object, time runs slower. This is not a metaphor or a simplification. It is a measured, confirmed, quantitative fact, precise enough that GPS satellites have to correct for it, or their positioning would drift by kilometers per day. The time distortion component of space-time curvature bends light by a certain amount. The equivalence principle gets you that far, but space-time is not just time. It is, and the name is doing real work here, space and time together as a unified geometry. And space itself also curves near a massive object in a way that is separate from and additional to the time curvature. The spatial curvature contributes an equal and independent amount of deflection to the path of a photon. Add them together, you get 1.75 arcseconds. Ignore the spatial part. Work with the equivalence principle alone, which is what both Soldner's framework and Einstein's 1911 paper effectively did, by different routes, and you get half of that. The second half required the full theory, the part that would take 4 more years, the part where space itself stops being a flat stage and starts being something that mass can bend, something with a geometry that changes depending on where you are and what's nearby and how much of it there is. The thought in the patent office was the beginning of all of that, not the destination, the beginning. A crack in a door that would eventually open into a completely different room, one where the floor isn't fixed and the geometry isn't given and the word straight means something more complicated and more interesting than it ever did before. The elevator is still there, conceptually, in the foundations of the full theory. You can still use it. You can still stand in the imaginary room and notice that you cannot tell from inside whether you're being held down by a planet or pushed up by a rocket. That indistinguishability never goes away. It just turns out to be the entrance to something much larger than it looks. What that larger thing is, what it actually means for space to have a geometry, for that geometry to curve, for curvature to be the mechanism behind everything gravity does. That's what the next part of this night is sitting with. Slowly, there's no rush. The geometry doesn't go anywhere. The paper Einstein published in 1911 has a title that sounds modest even by the standards of academic modesty. Translated from German, it reads, "On the influence of gravitation, on the propagation of light, 11 words, no fanfare." The kind of title that sits on a shelf and doesn't announce what's inside it, which is a prediction about starlight bending near the sun, a prediction that was specific enough to test, important enough to matter, and wrong by a factor of exactly 2. Not wrong in a sloppy sense, not wrong the way a careless estimate is wrong. Wrong in the way that a correct argument from incomplete premises is wrong, which is a different thing entirely and worth taking a moment with. By 1911, Einstein had been living with the equivalence principle for 4 years. The thought from the patent office that gravity and acceleration are locally indistinguishable, that a person in freefall feels no gravity, that these two facts are not separate observations but a single deep truth about the physical world, had settled into something more formal, more workable, more like a foundation than a feeling. He knew what it implied for light. He had worked through the elevator thought experiment in enough directions to be confident that gravity must bend light, that the bending was real, that it was in principle measurable. What he published in 1911 was that argument completed. The equivalence principle says, whatever acceleration does to light, gravity must also do, and acceleration, a room moving upward while a photon crosses it, produces an apparent downward curve in the photon's path, measurable as a displacement when the photon hits the far wall. This displacement has a size. The size depends on the acceleration, the width of the room, the speed of light. You can calculate it. Einstein calculated it. He then translated that calculation into the language of a gravitational field, specifically the gravitational field of the Sun, and produced a predicted deflection of light passing near the Sun's edge. 0.83 arcseconds. He also noted in the paper that this prediction could be tested during a solar eclipse, when stars near the Sun's edge would become visible, and their apparent positions could be compared to their known positions on nights when the Sun wasn't in the way. The comparison would reveal whether the positions had shifted, whether the light from those stars passing near the Sun had bent. This was, by any measure, a remarkable thing to publish. A specific, quantitative, empirically testable prediction about the behavior of light near a massive object, derived from a principle about the equivalence of gravity and acceleration. The whole chain of reasoning was tight. The math was correct. The prediction followed from the premises. The premises were incomplete. Here is the part that requires a kind of patience with ambiguity that doesn't come naturally. The equivalence principle, as a local statement, as a description of what happens in a small box over a short time, is correct. It is not the incomplete part. Gravity and acceleration are locally equivalent. That's right. What is incomplete is the picture of spacetime that the equivalence principle alone gives you access to. The equivalence principle lets you see what gravity does to time. And gravity does do something to time. Clocks run slower in gravitational fields, faster when they're farther from mass, and this effect is real and has been measured in laboratories and has to be corrected for in systems precise enough to care about it. The time part of space-time curvature is captured by the equivalence principle. That time curvature bends light. It contributes to the deflection. But space-time has a spatial part as well. Space itself, not just time but the geometry of distances and directions in the region around a massive object, also curves. And this spatial curvature is not accessible from the equivalence principle alone. It requires the full theory, the complete geometric framework that Einstein wouldn't finish until 1915. The part where the mathematical apparatus becomes heavy and the intuitions from thought experiments start to reach their limits. The 1911 paper had the time part. It was missing the space part. And the space part contributes an equal amount to the deflection. I keep coming back to the specific shape of that gap, the missing half, and finding it hard to categorize cleanly. There's a version of this story where it's straightforwardly a case of a theory being extended, refined, completed, and that's true, but there's something else in it too. Einstein knew by 1911 that the equivalence principle was a local statement. He knew that her more complete theory of gravity would have to be global, would have to describe not just what happens in a small box for a short time, but what happens across all of space-time, at every point, with a geometry that could vary from place to place and moment to moment. He was already working on that larger theory when he published the 1911 result. The larger theory wasn't done. He published the incomplete version because it was already testable, already important, already, in its own terms, correct, which it was from its own premises. The question of whether to publish a result you know is provisional, a result whose completeness you yourself doubt, whose underlying framework is still being built, doesn't have a clean answer. You could argue it both ways without either argument quite winning. Einstein published. The prediction sat in the literature. The test was proposed. The eclipse of 1914 was identified as a potential opportunity. Expeditions were planned, and then the war intervened and the measurements weren't made, which turned out to be fortunate, because if they had been made against the 1911 prediction, they would have confirmed a value that general relativity would later double. A provisional truth, tested too early, confirmed against the wrong target. There's the smell that old academic papers have when you print them from digital archives, slightly acrid. The ink from a laser printer still faintly warm, carrying nothing of the original document's century except the words. Reading Einstein's 1911 paper that way, in translation, there's a cleanliness to the argument that feels almost austere. No hedging, no visible uncertainty. The prediction is stated plainly, the method is laid out, the number is given. You would not know, from reading it, that the author understood it to be a step rather than a destination. Maybe that's just how papers are written. Maybe the form requires a certain confidence that the content doesn't always warrant. Or maybe Einstein genuinely believed in 1911 that 0.83 arcseconds was right. Maybe the incompleteness hadn't yet sharpened into a felt gap. He was building something large and he was in the middle of it. And from inside the middle of a large construction, you can't always see which parts are load-bearing and which parts will eventually need to be replaced. The number was right about one thing. Light bends near the sun. The amount it bends requires the rest of the theory, the part that took 4 more years, that replaced the intuition of the elevator with the full mathematics of a curved geometry that finally accounted for the space in space-time and not just the time. 1915 is where the number doubles, not because the argument changes, but because it deepens. The spatial curvature that the equivalence principle can't reach, the other half of what mass does to the geometry around it, gets included, and when it's included, the prediction becomes 1.75 arcseconds, and that prediction, tested in 1919 against the actual positions of stars during an actual solar eclipse, matches. The difference between 0.83 and 1.75 is not just arithmetic. It is the difference between a framework that knows what gravity does to time and a framework that knows what gravity does to everything. Time, space, the geometry of the region, the shape of the paths that anything moving through that region will follow, including light. Including massless light that the old framework had no clean way to touch. What that full framework actually says, what it means for space itself to have a geometry, for that geometry to vary, for the path of a photon to be determined not by a force but by the shape of where it is, that's the chapter this night has been building towards since it started. It needs more room than this. It needs its own space. Which is, it turns out, exactly the right word for what comes next. Somewhere around this point in most explanations of general relativity, a rubber sheet appears. You know the one. A large flat membrane stretched taut, and someone places a heavy ball in the centre, and the sheet sags and then smaller balls roll toward the centre, because the surface is no longer flat. It's in textbooks, in documentaries, in the kind of museum displays that have a coin funnel with a curved track and a sign that says this is how gravity works, and it is, in its own limited way, useful. But it's also wrong in a way that matters tonight. And since this chapter is specifically about what the geometry of space-time actually means, not as a teaching prop but as a physical reality, the rubber sheet has to go, not rudely, just firmly. The rubber sheet is a 2-dimensional surface curving into a 3rd dimension you can see. Space-time is a 4-dimensional geometry that curves into no additional dimension that any human being has ever accessed or can picture. The sheet gives you the impression that curvature is something you can observe from outside, from above, the way you can look down at a curved road from a helicopter. Space-time curvature is not like that. There is no outside, there is no above. The curvature is intrinsic. It's in the geometry itself, detectable from within the geometry, without reference to anything external. That's the thing that needs sitting with. Start somewhere more ordinary. A long, flat road. You're driving on it and the road curves to the right, and you feel the curve. The slight push of the seat against your left side, the steering wheel's resistance, the visual sweep of the horizon shifting. The curve is obvious. You're experiencing it from inside it, but you can also see the outside of it. The sky, the fields, the geometry of the road against the landscape. The curve has an inside and an outside, and both are accessible. Now imagine you cannot see outside the road. There is no sky, no fields, no horizon. There is only the road surface and your position on it. Can you still detect that the road is curved? Yes. With the right measurements, yes. On a curved surface, the rules of flat geometry break down in specific measurable ways. If you draw a triangle on a flat surface, the interior angles add up to exactly 180 degrees. On the surface of a sphere, a curved surface, a triangle's interior angles add up to more than 180 degrees. The excess isn't a mistake. It's a signature of the curvature. You don't need to see the sphere from outside to know it's curved. You just need to measure the triangle carefully enough. This is what mathematicians mean by intrinsic curvature. Curvature that's detectable from within the surface itself, without appeal to any external vantage point. And this is the kind of curvature that general relativity is talking about when it says space-time is curved near a massive object. Not curved into something you could point to. Curved in the sense that the geometry of distances and angles and durations behaves differently than it does in flat space. The rules change. The triangle's angles don't add up right. The ratio of a circle's circumference to its diameter isn't quite pi. The paths that look straight from the inside turn out, when followed long enough, to be arcs. The specific feeling of trying to hold this is, and I'm going to say this plainly, a bit like trying to grip something with your hands closed. The geometry is real. The mathematics is precise. But the intuitive picture keeps sliding, keeps wanting to be the rubber sheet, keeps wanting an outside view that isn't available. Maybe that's fine. Maybe that's actually the honest state to be in. Physics doesn't owe us the ability to picture everything. The universe is under no obligation to arrange itself in ways that a mammal brain, optimized over millions of years for navigating a physical environment that is neither very large nor very small nor very fast, finds easy to visualize. Some things are real and true and confirmed by every measurement anyone has ever made, and also genuinely resistant to the kind of spatial intuition that usually helps. Space-time curvature is one of those things. Here is a way into it that doesn't require a picture. Think about duration, not distance. Duration. The time it takes for something to happen. Near a massive object, time runs slower. Not slower in the sense that clocks are broken or that the perception of time changes. Slower in the sense that fewer ticks of a genuine, properly functioning clock occur per unit of coordinate time. And this has been measured, and the measurements match the predictions of general relativity to a precision that is frankly a bit unsettling. GPS satellites run their clocks slightly fast to compensate for the fact that they are farther from Earth's mass than ground-based clocks, and therefore experience time running slightly faster. Without the correction, GPS positioning would drift by roughly 11 kilometers per day. Time itself, not the measurement of time, but time, runs at different rates in different gravitational environments. Now, A photon moving through a region where time runs unevenly, faster on one side, slower on the other, will take paths that account for that unevenness. The side where time runs slow is, in a precise geometric sense, shorter in the space-time interval. The photon, following the geometry, drifts toward that side. This is what the time curvature component of space-time does to a light path. This is the half that the equivalence principle captures. This is Soldner's half, Einstein's 1911 half. But the other half, the spatial part, the way the geometry of distances themselves shifts near a massive object, independently of time, this is harder to find an entry point into, and I want to be careful here not to reach for a comparison that flattens it into something it isn't. What I can say is this: the geometry of space near a massive object is not Euclidean. The rules of flat geometry don't hold. If you were to stretch a ruler near a very massive object and measure distances carefully, then compare those measurements to what flat Euclidean geometry would predict, there would be a discrepancy. Not a large one in everyday life, not detectable without instruments sensitive enough to pick up what are, at human scales, extraordinarily small deviations, but near neutron stars, near black holes, near objects dense enough that the curvature becomes significant, the discrepancy is real, it matters, and it contributes to the path a photon follows. Both curvatures together and time and space give you the full deflection. There is a particular kind of exhaustion that comes from trying to think about something that doesn't fit any existing shape in the mind. It's not the exhaustion of confusion exactly, more like the sensation of mental muscle strain, the feeling of reaching and not quite closing the hand. I notice it around this point, personally, every time I try to follow this all the way through, without letting an analogy take over and do the work for me. The analogy always wants to. The rubber sheet is right there, patient, offering its comfortable, incorrect picture of a ball rolling toward a dimple in a fabric. And it's tempting. It provides relief. But the dimple in the fabric is embedded in a higher dimension you can point to. The curvature of space-time is not. What the full geometry gives you, when you let the mathematics do what it does without insisting on a visual, is a description of how the interval between events changes depending on where you are relative to mass. The interval is a kind of combined measure of distance and duration, and it's the thing that's actually invariant in relativity, not distance alone, not time alone, but the space-time interval between two events, near a massive object. The way the interval is composed changes. Spatial distances and time intervals combine differently than they do in flat space-time. And this change combination, this loosely altered geometry, is what determines the paths that things follow. All things, not things with mass, not things with charge, all things, a photon with no rest mass at all, moving through a region of curved space-time near a galaxy, follows the geometry just as faithfully as a planet in orbit, or a clock running slow, or a GPS satellite correcting for relativistic time dilation. The geometry doesn't ask about mass before it applies. The geometry is just the shape of where things are, and things follow the shape. This is, when you stay with it long enough, a genuinely strange feature of reality. Not strange in a sensational way, strange into the way that a room looks strange when you've been staring at it too long, and the familiarity starts to lift and you see the actual shapes of the furniture without knowing what they're called. Gravity is not a force that reaches between things. It is the shape of where things are, and the shape is intrinsic. No outside view, no rubber heat, no additional dimension to point toward. Just the geometry, available only from within, detectable only through measurement, and real in a way that has been confirmed by every instrument sensitive enough to check. The next thing to understand is what a path through that geometry actually looks like. not as an abstract curve, but as the specific thing that free-falling objects, photons included, follow when nothing is pushing them. There's a word for it. The word is geodesic, and it means something more precise and more interesting than it first sounds. That's where this goes next. Walk in a straight line, not on a road, not following a path someone else made, just pick a direction and walk. On a flat, featureless surface, this is easy. You keep your eyes on a fixed point ahead, you don't deviate, and the line you trace is straight in every sense the word has. Straight as measured by a ruler. Straight as described by geometry, straight in the way that requires no further qualification. Now try it on a hillside. Not a gentle slope, a real hillside, uneven, with rises and drops that pull your weight sideways, with ground that tilts under one foot and not the other, with the specific muscular work of constantly correcting for a surface that isn't cooperating. You're still trying to walk straight. You're still picking a point and moving toward it. But the line you trace when viewed from above is not what flat surface straight looks like. The surface has intervened. The geometry of where you are has changed what straight means in practice, even though your intention hasn't changed at all. This is somewhere near the idea of a geodesic. Not the whole idea, but somewhere near it. A geodesic is, technically, the straightest possible path between 2 points in a given geometry. In flat space, the Euclidean space of ordinary intuition, the geodesic between 2 points is a straight line, simple. In curved space or curved space-time, the geodesic is still the straightest possible path. But what that path actually looks like traced out in coordinates can appear to curve, appears to from some perspectives, is straight in the geometry's own terms. The distinction between those two descriptions, appears curved is straight, is the thing worth sitting with for a moment. When a planet orbits a star, the standard story is that gravity is pulling it inward, creating a curved path around the star, and the planet keeps going around because the pull is constant and the planet's forward momentum keeps it from falling all the way in. This is Newton's story. It's a story about a force producing a deviation from straight line motion. Einstein's story is different. In Einstein's story, the planet isn't being pulled. The planet isn't deviating from straight line motion. The planet is following the straightest available path through a space-time that has been curved by the star's mass. From outside, from a coordinate system far from the star where space-time is approximately flat, that path looks like an ellipse. But in the local geometry, in the curved space-time the planet is actually moving through. It's doing the equivalent of walking as straight as it can on the hillside. The surface is curved. The path follows the surface. That's not deviation, that's fidelity. A geodesic in curved space-time is what you get when nothing is pushing you. No force, no intervention, just the geometry. And a particle following it as faithfully as it can. There's a technical split here that's easy to miss but matters. In flat space-time, no gravity, no mass nearby, the space-time of special relativity, there are two kinds of geodesic. Time-like geodesics, which are the paths followed by massive particles, things with rest mass that can never reach the speed of light. And null geodesics, which are the paths followed by massless particles, photons specifically, moving at exactly the speed of light. The difference between them is in a quantity called the space-time interval. For a massive particle's path, the interval between any two events on the path is time-like. There is a well-defined proper time ticking along the path, a duration the particle itself experiences. For a photon's path, the interval is exactly zero. Always, between any two events on a photon's trajectory, the space-time interval is null. Not small, not negligible, 0. This sounds strange, and it is strange. It means, in a specific technical sense, that a photon doesn't experience the passage of time between emission and absorption. Not slowed time, not dilated time, no time at all in the photon's own frame, if a photon can even be said to have a frame, which is already a question that gets complicated fast and is better left slightly open than forced into a neat answer. What matters for the bending of light is that photons follow null geodesics, and null geodesics in curved spacetime are curves. In the coordinate sense, curves. In the geometric sense, the straightest available path through a geometry that isn't flat. The unnecessary detail I keep thinking about whenever this comes up, and I'm not sure why it sticks, it just does, is what fresh asphalt smells like on a hot day. That specific sharp petrochemical smell that sits in the air above a newly paved road, almost visible in the heat shimmer. Roads are straight where engineers made them straight, and they curve where the terrain insisted on it, and the driver doesn't always know which is which from inside the car. The straightness is imposed, the curves are negotiated with the ground. Geodesics aren't imposed or negotiated, they're what's left when nothing imposes anything at all. In curved space-time near a massive object, a star, a galaxy, a cluster of galaxies, the null geodesics, the natural photon paths, curve. Not because something is pulling the photons, because the paths themselves, the straightest available paths through that specific geometry, are not what flat space-time straight looks like. A photon near the Sun follows a null geodesic that, expressed in our flat-looking coordinates, bends by 1.75 arcseconds as it grazes the Sun's edge. That number, 1.75 arcseconds, comes from calculating the null geodesic in the Schwarzschild geometry, which is the solution to Einstein's field equations for the space-time around a single, spherically symmetric non-rotating mass. The calculation accounts for both the time curvature component and the spatial curvature component. Both halves. The full geometry. Soldner's calculation gave you the geodesic in flat space with the Newtonian force attached. Einstein's 1911 calculation gave you the time curvature part of the geodesic in curved spacetime. The full general relativistic calculation gives you both, and the result is twice Soldner's number, and that result matches every measurement that has ever been precise enough to check. The hillside metaphor has done what it can. Let it go. What's actually happening when light bends near a massive object has nothing to do with walking, with hillsides, with the muscular effort of staying upright on uneven ground. Those were entry points, handholds on the outside of an idea that doesn't have an outside. What's actually happening is this: a photon with no rest mass, subject to no force, moving through a region of space-time whose geometry has been altered by the presence of mass, follows the straightest available path through that geometry. The path, expressed in coordinates that assume flat space, looks curved. The path, understood in the geometry's own terms, is straight. Gravity doesn't reach out and bend it. The geometry bends. The photon follows the geometry. Those are not two events, they are one. The 1919 eclipse turned this from a geometric argument into a measured fact. Expeditions, photographs, stars appearing where they shouldn't, displaced from their expected positions by the bending of their light around the sun. The measured displacement matching the full general relativistic prediction, not Soldner's half, not Einstein's 1911 half, but the complete value that the complete theory predicted. That moment, the photographs, the comparison, the match, is where this moves next, not the triumph of it, not the headline. The specific texture of what it meant to test this particular prediction at this particular time with the instruments available in the conditions that existed. That's a chapter that deserves to start fresh. The island of Príncipe sits in the Gulf of Guinea, off the western coast of Africa, close enough to the equator that the seasons don't announce themselves the way they do further north or south. In May, it is warm in the specific way that equatorial islands are warm, not the aggressive heat of a desert, but a damp, settled warmth that gets into fabric and wood and stays there. The kind of warmth that makes precision instruments fussy, the kind that makes the air above hot surfaces shimmer in ways that are unhelpful if you're trying to take careful photographs of stars. Arthur Eddington arrived there in the spring of 1919 with telescopes, with photographic plates, with the specific logistical weight of a scientific expedition that had been planned for months and depended on a window of totality that would last roughly 6 minutes. He was there because of a number. Not 1.75 arcseconds exactly. That number had existed in the literature since 1915, but it was a prediction, not a fact. And the difference between a prediction and a fact is the entire enterprise of experimental physics. He was there because a total solar eclipse offered the only practical opportunity to photograph stars close to the sun's edge, and photographing stars close to the sun's edge was the only way to check whether their apparent positions had shifted. Shifted by the amount that curved spacetime around the sun's mass would shift them. If curved spacetime around the sun's mass was a real thing, and not an elegant piece of mathematics that happened to be wrong. The second expedition was in Sobral, Brazil. 2 teams, 2 locations, the kind of redundancy that acknowledges, without saying so directly, how much can go wrong. What can go wrong with a solar eclipse observation is mostly weather. Clouds are the obvious one. A total solar eclipse at the wrong moment of a cloud's drift across the sky is just darkness, and then light again, and a set of photographic plates that recorded nothing useful. There is no rescheduling. The geometry of the solar system does not accommodate scientific convenience. You are there on that day, at that time, with those instruments, and the sky either cooperates or it doesn't. The morning of May the 29th, 1919, Príncipe had clouds. Eddington wrote about this afterward. The waiting, the overcast sky, the specific quality of that kind of morning tension which is different from ordinary anxiety because there is nothing to do with it. No action available, just the watching. The clouds didn't clear entirely. During totality there were clouds. Some of the photographic plates recorded nothing. Some recorded stars through gaps in the cover, partial exposures, images of uncertain quality. 16 plates were taken. Most were compromised. A small number were usable. From those usable plates, Eddington extracted measurements of stellar positions. He compared them to positions recorded on reference plates taken months earlier, when the sun wasn't nearby, when the stars could be photographed without any gravitational lens between them and the telescope. The comparison showed a displacement. The displacement was close to what Einstein had predicted. Close is doing some work in that sentence, and it's worth saying so. The measurements from Príncipe gave a deflection value with an uncertainty range that included Einstein's prediction. The measurements from Sobral, where conditions had been somewhat better, though not without their own problems, a mirror coelostat that warped slightly in the heat and introduced its own systematic errors, gave results that were in better agreement with the full general relativistic value. The combined result was announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6th, 1919. The newspapers called it a revolution. The Times ran the headline, "Revolution in Science," the following day. Einstein became, in a matter of weeks, something that theoretical physicists very rarely become, a household name, a public figure. recognizable to people who had no particular interest in physics and no framework for understanding what he had actually done. The measurements themselves were less clean than the headline suggested. There were error bars. There were systematic uncertainties. Some scientists at the time raised legitimate questions about whether the data unambiguously distinguished Einstein's prediction from Newton's half-value. Those questions weren't entirely wrong. The 1919 data, by modern standards, was marginal. Confirmation came more solidly in subsequent decades, with better instruments, radio interferometry, and eventually satellite observations that were precise enough to rule out the Newtonian value by a factor of hundreds. But in 1919 it was enough. I find myself thinking about the photographic plates more than about the announcement. Glass plates, coated with a light-sensitive emulsion, loaded into a telescope on a warm island while clouds moved overhead, exposed for a few minutes during the brief totality of a solar eclipse, and then carried back to England to be measured with a micrometer. The measurement process was painstaking. Each stellar image located precisely on the plate, its position compared to the reference plate, the difference calculated, the deflection inferred from a set of differences across multiple stars. This is how you find out whether space-time is curved. Not with a thought experiment, not with an equation, not with a conference presentation, with glass plates and emulsion and a micrometer, and the willingness to travel to an equatorial island and wait in the heat for 6 minutes of totality and hope the clouds move. There's something about that physical chain, the mathematics of curved space-time translated eventually into the position of a star on a glass plate, that I find difficult to fully absorb even after thinking about it for a long time. The abstraction and the concreteness of it, the idea that a curvature in the geometry of the universe shows up finally as a displacement you can measure with a mechanical device on a piece of coated glass. What the 1919 results confirmed, however marginally, however subject to the caveats that careful scientists raised then and raise now, was that light bends near the sun by an amount consistent with general relativity and inconsistent with the Newtonian prediction. The geometry of space-time around a massive object alters the paths that light follows. The alteration is real, measurable, and of the specific magnitude that the theory built on the equivalence of gravity and acceleration, on intrinsic space-time curvature, on null geodesics in a non-Euclidean geometry predicts, not the half-value, the full value. Both halves of the curvature, time and space, showing up in the positions of stars on glass plates on a cloudy island morning in 1919. It didn't become perfectly confirmed that day. That took decades more. But it became something other than pure theory. It became a number that had been looked for in the real sky by real instruments, on a real island with real clouds and a real micrometer, and found approximately where the geometry of space-time said it should be. Light bends by that amount near that mass. The rule from Chapter 1, the furniture rule, the unexamined assumption that gravity acts only on mass, that massless light should pass by unaffected, had been by this point not merely questioned but measured against the alternative and found to be wrong. Not everywhere, not in the everyday physics of dropped cups and rain going downward, but in the regime where mass is large enough and light passes close enough and instruments are sensitive enough to see the difference. Wrong, half right. Capturing one layer of a reality that has two, what remained after 1919 was to understand more precisely what had been confirmed. Not just that light bends, but why. Not just that the number matches, but what the number means, what kind of universe produces it, and what else that universe implies. Some of those implications arrive slowly. Some are still arriving. The rings are one of them. perfect circles of light in the sky that Einstein calculated and then dismissed as unobservable, and which turned out to be everywhere. Einstein didn't think anyone would ever see it. That part is easy to forget, given how the story usually gets told, the prediction, the confirmation, the triumph of geometry made visible. The cleaner version skips over the fact that Einstein himself, in 1936, published a short paper in the journal Science, calculating what would happen if two stars aligned perfectly along the line of sight from Earth, one behind the other, with the foreground star acting as a gravitational lens for the light of the background star. He did the calculation. He got the geometry right, and then he wrote in the same paper that the phenomenon would be too small to observe, the image splitting too fine, the alignment too unlikely, the instruments of the day nowhere near sensitive enough to detect an effect of that magnitude. He published it, apparently, only because a Czech engineer named Rudy Mandl had written to him repeatedly asking him to work it out. Einstein did the calculation as a kind of courtesy. He noted, with what reads as mild impatience, that there was not much practical value in the result. He was wrong about that. The math, though, the math was right. When a massive object sits precisely between a light source and an observer, precisely in the sense of perfect or near-perfect alignment along a single line, the gravitational bending doesn't deflect the light to one side or the other. It bends it symmetrically in every direction at once, curving light from above, below, left, right, all of it equally, all of it by the same geometry, all of it arriving at the observer's position having been bent around the lens from every angle simultaneously. The result, if the alignment is exact, is not a point. It is not a smear. It is a circle. A thin luminous circle surrounding the lensing object, formed entirely from light that originated behind it and was bent around it by the curvature of space-time. Light that, without the lens, would never have reached the observer at all. The first time I really looked at an image of one of these, not a diagram, not an illustration, an actual telescope image, I had the specific disorientation that comes from seeing something that looks designed in a context where design has no meaning. There's a faint, dusty smell that old printed astronomy papers have, the kind you find in university libraries in the sections nobody visits anymore. And I was sitting with one of those, and there was a photograph. And in the photograph was a circle of light around a galaxy, and the circle was almost perfect, and for a moment the brain just refused it, filed it under artifact, assumed a lens flare, or a printing error, or something introduced by the equipment. It wasn't any of those things. It was light from a galaxy billions of light years away, bent into a circle by the mass of a galaxy billions of light years closer, arriving at a telescope on Earth in the shape of a ring because the geometry of space-time between source and observer happened, at that particular alignment, to curve equally in every direction. Einstein called this effect theoretical, unobservable, of limited practical interest. The first confirmed observation came in 1988. A radio source, MG1131+0456, observed with the Very Large Array, showing two similar images stretched into an almost complete ring, then more, then many more, then with the deployment of better instruments, something closer to a flood. The James Webb Space Telescope spent 255 hours pointed at a single region of sky containing roughly 42,000 galaxies. The Cosmos Webb Survey it was called. Among the things it found were more than 400 candidate Einstein rings, some partial, some nearly complete, some so geometrically clean they looked like they were drawn with a compass. 400 in one patch of sky, each one an accident of alignment, each one requiring a background source, a foreground mass, and an observer positioned along a line connecting the two with enough precision that the bending is symmetric. The probability of any single alignment being that precise is low. The universe is large enough that low probabilities produce hundreds of examples in a field of 42,000 galaxies. But the rings aren't just, I almost want to say they aren't just beautiful, but that's not the right frame for this. Beauty isn't really the point, or at least it isn't the interesting part. The interesting part is what they contain. Light that has been bent into a ring has travelled from its source to the lens to the observer along a path it would not otherwise have taken. In many cases, the background galaxy producing the ring is so distant, so faint, that without the gravitational lens amplifying and redirecting its light, it would be completely invisible from Earth. The lens acts as a natural telescope gathering light that would have dispersed past us, and concentrating it into something detectable. Some of the rings imaged by Webb contain light from galaxies that existed when the universe was less than 1 billion years old. The era of rionization, the period when the first stars and galaxies were forming, when the universe was transitioning from a fog of neutral hydrogen into something more transparent, is a period that is effectively inaccessible to direct optical observation. The light from that era is too faint, too distant, too redshifted. Unless something very massive happens to sit between that era and us, bending the light around itself and sending it our way. The rings are windows. Unscheduled, unplanned, geometrically inevitable windows into parts of the universe that would otherwise be simply gone from view. Einstein's 1936 paper dismissed the practical value of this. It's hard to blame him. In 1936, the instruments didn't exist. The radio telescopes that would find the first ring were 50 years away. The space telescopes that would find 400 candidates in a single survey were almost 90 years away. From where Einstein was standing, the calculation was a theoretical exercise requested by a persistent amateur, and the result was too small and too unlikely to matter to observational astronomy. What he couldn't see from 1936 was the scale at which the universe would eventually be surveyed. He was thinking about stars lensing other stars, stellar mass lenses producing micro-arcsecond image splittings far below any threshold of detection. He wasn't thinking about galaxy clusters, masses billions of times larger than any star, producing image splittings large enough to see clearly in optical telescopes. The geometry scales with mass. Bigger lens, larger ring, more detectable. Galaxy clusters produce rings you can photograph. He didn't quite get there. The window metaphor has been sitting in this chapter without being named, so let it be named now and then let it go. A ring is a window in the sense that it shows you something behind an obstacle. Light rerouted around a mass that would otherwise block it entirely. But windows imply architecture, intention, a frame built for a purpose. These rings have none of that. They are purely geometric. They exist when 3 points align and the intervening mass is large enough, and the space-time it curves is curved enough, and the geometry does what the geometry does, with complete indifference to whether anyone is watching. The window just is when the conditions are met. And the conditions are met, it turns out, in hundreds of places in a single patch of sky, if you look carefully enough and long enough. The rings also do something that nothing else quite does in observational astronomy. They reveal mass that doesn't shine. The amount of bending, the precise radius of the ring, the way the background light is distorted, all of these depend on the mass of the lensing object. Not the luminous mass, not the stars and gas and dust that emit detectable radiation. The total mass, everything, including whatever is there that produces no light at all. Dark matter leaves no direct electromagnetic signal. It doesn't emit, absorb, or scatter light in any way that has ever been measured. but it has mass, and mass curves spacetime, and curved spacetime bends light, and bent light in the right alignment forms a ring whose geometry carries a precise record of how much mass produced it. The rings are, among other things, dark matter maps, worn by the light, in circles, around things that cannot be seen. There is something in that chain, the invisible mass, the curved geometry, the bent light, the ring on a photographic plate, that feels like it should be surprising every time it's thought about. Maybe it becomes familiar with repetition, maybe it doesn't. The next chapter is about what happens when you take all of this, the geometry, the bending, the rings, the confirmed predictions, and push it to its edges, to the place where general relativity meets a regime it wasn't built for, and where the mathematics that explains everything in this chapter quietly stops being able to explain everything. General relativity is, by any reasonable measure, one of the most successful physical theories ever written down. That sentence feels almost too smooth to be useful, so it's worth making it specific. The theory predicts the precession of Mercury's orbit, a small stubborn wobble that Newtonian gravity couldn't account for, to extraordinary precision. It predicts gravitational time dilation, confirmed in laboratories, in satellites, in the daily operation of GPS systems that would drift by kilometers per day without the relativistic correction built into their clocks. It predicts gravitational waves, ripples in the geometry of space-time itself, produced by massive accelerating objects, which were detected directly in 2015, a century after the theory was written, by instruments sensitive enough to detect a displacement smaller than 1/10,000th the diameter of a proton. It predicts light bending, ring formation, the existence and properties of black holes, the expansion of the universe. Every prediction that has been tested has been confirmed, every single one, and yet there is a regime where the theory quietly stops working. Not loudly. General relativity doesn't crash or produce obviously nonsensical numbers in the way that a broken model sometimes does. It produces infinities. At the center of a black hole, the equations push toward a singularity, a point where density becomes infinite, where space-time curvature becomes infinite, where the numbers go to values that no physical measurement could ever record, and where the theory is, in the language physicists use for this situation, breaking down. Breakdown doesn't mean wrong exactly. It means the theory is being applied outside the domain where it's valid. A thermometer measures temperature accurately across a wide range, and then, at the extreme, stops being a reliable instrument. It's not that temperature ceases to exist at those extremes, it's that the instrument wasn't designed for them. General relativity is an instrument designed for the large and the massive. Space-time curvature, gravitational fields, the geometry of the universe at cosmic scales, this is its territory. And in its territory it is precise and reliable to a degree that is, if you think about it carefully, almost unreasonably good. The regime it wasn't designed for is the very small. Quantum mechanics handles the very small. It describes the behavior of particles at atomic and subatomic scales with a precision that rivals, in some cases exceeds, the precision of general relativity at large scales. The magnetic moment of the electron, calculated using quantum electrodynamics and measured experimentally, agree to more than 10 decimal places. That is not an approximation. That is a theory correctly describing a physical quantity to 10 significant figures. Two theories, both extraordinarily precise, both confirmed by every experiment sensitive enough to test them, both describing the same physical universe. They don't fit together. This is the part I find genuinely difficult to sit with, and I want to be careful not to make it sound more dramatic than it actually is day to day in the life of a working physicist, because mostly it isn't dramatic at all. Most physics problems don't require you to simultaneously apply both theories, and in the regimes where each theory applies, each theory works, and the incompatibility stays quietly in the background like a low hum you learn to ignore. But it's there. The incompatibility is structural. Quantum mechanics describes forces through the exchange of particles, the electromagnetic forces mediated by photons, the strong nuclear force by gluons, the weak force by Z bosons. In quantum field theory, forces are not smooth fields pervading space. They are interactions, discrete exchanges, quantized. The expectation and the assumption that guided decades of work was that gravity would eventually submit to the same treatment, that there would be a graviton, a particle mediating gravitational interactions, and that a quantum field theory of gravity would be writable in the same way that quantum electrodynamics is writable. Hasn't worked out that way. The naive attempt to quantize general relativity, to apply the mathematical procedures that worked for electromagnetism, produces infinities that cannot be removed, not the useful infinities of quantum electrodynamics, which can be handled by a procedure called renormalization. Intractable ones. The theory resists quantization in a way that suggests the resistance is not a technical problem to be solved by the better mathematics, but something more fundamental, a sign that the framework itself needs to be replaced by something that doesn't yet exist. There's a specific smell in hospital waiting rooms that has nothing to do with medicine, something plasticky, slightly warm, the smell of chairs that have been sat in by many people over many years. I thought about this once, reading about the incompatibility problem in a paper that was simultaneously very precise and very honest about how little was resolved. And I'm not sure why the association formed. Maybe just the quality of waiting. The sense of something that hasn't arrived yet and might not for a long time. Quantum gravity, the framework that would reconcile general relativity and quantum mechanics, that would describe what gravity does at the scale where quantum affects matter, has been actively sought since at least the 1930s. String theory, loop quantum gravity, causal dynamical triangulations, and a dozen other approaches have been proposed, developed, refined, argued over. None has produced a confirmed prediction that experiment has been able to test. None has achieved the status of being wrong, which is in physics actually a meaningful milestone, a sign that a theory has become specific enough to be checked. Is that a failure? It might be too early to say. The history of physics has long latency periods between the recognition of a problem and the arrival of the framework that resolves it. The mathematical tools needed for general relativity took decades to develop after the problem was posed. Maybe quantum gravity is waiting for mathematics that hasn't been invented yet. Maybe. That's not a reassuring answer, but it might be the honest one. Here is the specific edge where light bending sits in relation to all of this. The photon that curves around a galaxy, the one that forms the rings described in the last chapter, the one whose path is a null geodesic through curved spacetime, is described by general relativity. The bending is a classical effect, a consequence of the large-scale geometry of spacetime, and the classical description works. It matches observation. There is no quantum correction needed at this scale, no regime where the photon's quantum nature interferes with the geodesic calculation. But the photon is also a quantum object. It has a frequency, an energy, a polarization. It was emitted by a quantum process, an electron transitioning between energy levels, or a more complex quantum event in a hot, dense astrophysical environment. It will be absorbed by a quantum process. In between, While it travels through curved spacetime following a null geodesic, the quantum nature of the photon and the classical nature of the spacetime it's traveling through are not in conflict exactly, but not fully unified either. The photon obeys quantum mechanics. The spacetime obeys general relativity. These two descriptions coexist in the regime of light bending around galaxies without immediately breaking anything. The scales are such that the incompatibility stays in the background, unhurried, not yet urgent. But push further. Go to the places where the geometry becomes extreme, to the singularity at the center of a black hole, to the first moments after the Big Bang, to any physical situation where both quantum effects and gravitational effects become simultaneously important, and the coexistence stops being comfortable. The two frameworks pull in different directions, and there is currently no third framework to resolve the tension. What gravity is actually doing, the deep answer, the one that would connect the curvature of spacetime to the discrete quantized world of particles and fields, is not known. General relativity says, gravity is the curvature of spacetime, and curvature is produced by the distribution of mass and energy, and everything moves through the curved geometry along geodesics, and that's what gravity is. Smooth, continuous, geometric. Quantum mechanics says, everything is discrete at small enough scales, interactions are exchanges of quanta, fields are quantized, and there is no smooth continuous background. Spacetime itself at the Planck scale might be grainy or foamy or something else entirely, some structure that neither theory currently describes. Both of these are right in their domains. What happens at the boundary of those domains is an open question that's been open for almost a century and shows no clean signs of closing. The light that bent around the Sun in 1919, displacing those stars on Eddington's photographic plates by 1.75 arcseconds, that light was a quantum object travelling a classical path through a geometry that two of the most successful physical theories ever written cannot fully agree on at their shared boundary. It bent correctly, the measurement matched the prediction, and the prediction came from a theory that somewhere beneath the scales, where its predictions can be tested, runs out of ground to stand on. That's not a flaw in the story, it's just where the story actually is, right now, in the year that this is being said. The theory works. It works extraordinarily well. And it also has an edge, a place where it meets something it can't fully describe, and that edge is real. And physicists know where it is, and nobody has crossed it yet. The light bends, the geometry curves, the rings form in the sky, and underneath all of it, at the scale no instrument has yet reached, something is happening that no one has yet found the language for. There is a specific quality to confirmation that accumulates slowly, not the moment of it, the 1919 announcement, the newspaper headline, the joint meeting of the Royal Society where the results were read out and a century of Newtonian certainty quietly began its renegotiation. That moment has its own texture, already described. What comes after that moment is different. What comes after is the long, unglamorous process of checking again, and then checking again, with better instruments, in different ways, at different scales, asking the same question with more precision and seeing whether the answer holds. It held. The decades after 1919 added confirmation the way sediment adds to a riverbed, layer by layer, each layer thin, none of them dramatic on its own. Radio interferometry in the mid-20th century measured the deflection of radio waves from distant quasars as they passed near the Sun, with a precision that optical telescopes couldn't approach. The results matched general relativity. Radar ranging, bouncing radio signals off planets and measuring the delay as the signal passed near the Sun, the extra time caused by the curvature of spacetime slowing the signal's progress. matched general relativity. The Hipparcos satellite, operating from 1989 to 1993, measured stellar positions across the whole sky with enough precision to detect the sun's gravitational deflection of starlight, even from stars nowhere near the sun's edge, and matched Einstein's prediction to within 1 part in 1,000. 1 part in 1,000. From a satellite, measuring stars at right angles to the sun, each of these confirmations was, in isolation, a paper, a result. A number compared to a prediction found to agree, filed in the literature and moved on from. None of them produced a newspaper headline. None of them made Einstein more famous than he already was. They just added up, quietly, over decades, into a body of evidence that is, by now, so redundant in its agreement that the question of whether general relativity correctly predicts the bending of light is not really a live scientific question anymore. It does. It has been confirmed so many times, at so many scales, with so many different instruments and methods, that the confirmation itself is no longer the interesting part. What became interesting somewhere along the way was what the confirmation made possible. A confirmed theory is a tool. Once you know the light bends by a predictable amount near a predictable mass, you can use the bending to do things. You can measure masses you couldn't measure otherwise. You can see things you couldn't see otherwise. You can use the geometry of the universe as an instrument, not built by anyone, not calibrated by anyone, just sitting there in the distribution of mass across billions of light years, bending light according to rules that are now understood well enough to be worked backwards. Given the shape of a bent image, you can calculate the mass that bent it. Given the radius of a ring, you can calculate the mass inside the ring, all of it, luminous or not. Given the distortion pattern of background galaxies behind a cluster, you can map the distribution of mass in the cluster, including the mass that emits no light, the dark matter that has no electromagnetic signature and can only be detected currently by what it does to the geometry of space-time around it. Gravitational lensing became, somewhere between 1919 and now, one of the primary tools of modern cosmology, not a curiosity, a tool. The James Webb Space Telescope launched in December 2021. It reached its operating position, a gravitationally stable point about 1 million miles from Earth, on the side away from the Sun, and began observations in 2022. Its primary mirror is 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments that unfolded after launch. It observes primarily in infrared, which allows it to see through dust that blocks optical light and to detect light from objects so distant and so redshifted that their emissions have stretched from visible wavelengths into the infrared by the time they arrive. The gold-coated segments have a specific quality in photographs, a deep, almost amber warmth that is entirely a consequence of gold's optical properties and has nothing to do with aesthetics, but produces an instrument that looks, in images, like something that should be in a museum. What matters for this chapter is what it found when it looked at a particular region of sky for 255 hours. The Cosmos Web Survey, 42,000 galaxies in a single field. Systematic search for strong gravitational lensing. More than 400 candidate Einstein rings identified. Some partial arcs, some nearly complete circles, some as geometrically clean as anything a textbook diagram would show. 400. That number sat with me for a while after I first encountered it, in the way that numbers sometimes do when they're larger than the mental category you are holding them in. Einstein in 1936 had calculated the effect for stellar mass lenses and concluded it would be essentially unobservable. He was imagining star-sized lenses, arc-second scale alignments, instruments nowhere near sufficient. He wasn't imagining galaxy cluster mass lenses, or space telescopes with 6.5-meter mirrors, or surveys that look at 42,000 galaxies at once and have algorithms trained to find the geometric signatures of lensing in the images. 400 rings in one field, each one a consequence of the same physics, the same curvature, the same geodesics, the same null paths through a non-Euclidean geometry that a man in a patent office in Bern began working out in 1907 and spent 8 more years completing. Some of the rings in the Cosmos Web survey contain light from galaxies that existed when the universe was less than 1 billion years old. The universe is approximately 13.8 billion years old. 1 billion years in is early enough that the first large structures were still assembling, early enough that the process of reionization was either underway or recently completed, early enough that what we would now recognize as a galaxy was still something more provisional, more ragged, less settled than the galaxies visible in the nearby universe. That light, from that era, from those provisional early structures, has been travelling for nearly 13 billion years. It has passed through the expanding universe, been stretched by the expansion, arrived in our vicinity so faint and so redshifted that direct detection would be effectively impossible with any current instrument, except that on the way here, some of it passed close enough to a massive foreground galaxy that the space-time around that galaxy bent it, focused it, redirected photons that would have passed on either side of the observer's position and curved them inward toward the telescope, amplified by the lens into something detectable. The ring on the detector is ancient light, gathered by geometry. Light that should, by the ordinary accounting of distances and faintness, simply not be available to us. Made available by a gravitational lens that was sitting in the right place, curving space-time the right amount at the right angle for the photons to find their way here. This is the part that loops back quietly to where this all started. Chapter 1 was about a rule, the furniture rule. Gravity pulls on mass, light has no mass, light should be unaffected. That rule, checked against reality, is off by a factor of 2 even in its best Newtonian form, and off in kind, not just in amount, once the full geometry of space-time is understood. Gravity doesn't pull on mass. Gravity curves space-time. Everything that moves through space-time, massive or massless, fast or slow, particle or wave, follows the curvature. Light follows the curvature. Light has always followed the curvature. And that following, that obedience to a geometry shaped by mass, is what produced the rings in the Cosmos Web field. 400 of them, each one a window into something that would otherwise be invisible. Each one a consequence of a physical fact that sat unnoticed inside a comfortable, functional, slightly incomplete rule for 200 years before someone found the gap in it. The gap turned out to contain the shape of the universe. There's a tiredness that comes sometimes at this point in a long night of thinking about something large. Not the bad kind, Sopung. The kind that comes after a thing has been properly followed, when the mind has gone far enough that coming back feels like a real distance. The cup still falls in the kitchen, the floor still holds, the pressure of the mattress or the chair, whatever it is still there. The interrupted fall, the force that isn't gravity but is gravity's consequence, the thing you feel without thinking about it. The light from those early galaxies, bent into rings, is arriving right now, this moment. Photons that left their source almost 13 billion years ago, curved by a gravitational lens, somewhere in the intervening distance, landing on a detector in space that was built by people who understood, precisely enough to use it as a tool, why light bends when it has no mass. The rule was furniture. The universe, it turns out, had different furniture entirely. and we are only now, slowly, with instruments that unfold like flowers in space and look for 255 hours at a single patch of sky, beginning to read the inventory. General relativity has a boundary, not a wall. That image implies something abrupt, a surface you can press your hand against and feel pushed back. It's less definitive than that, more like walking on ground that becomes gradually less reliable underfoot. Solid for a long time, solid enough that you don't think about it. And then at some point you notice the ground has a quality it didn't have before, a slight give, an unevenness. A sense that the thing you're standing on is no longer quite as certain as it appeared from a distance. That's closer to what the boundary of general relativity feels like, as a conceptual situation. The theory works at every scale that has been tested. It works for light bending around single stars, for the orbital decay of binary pulsars, for the geometry of the observable universe, for the behavior of black holes as observed through their effects on surrounding matter. Every instrument built to check it has checked it and found agreement. This is not a theory in trouble at the scales it was designed for. It is, at those scales, one of the most precisely confirmed scientific frameworks ever developed. The trouble is elsewhere, in a regime that no instrument has yet reached, and may not reach in any near future, and that currently exists only as mathematics, the regime where the length scales are so small, the energies so large, the curvatures so extreme that quantum effects and gravitational effects become simultaneously important. The Planck length, 1.6 times 10 to the power of negative 35 meters. To give that number a sense of scale that is probably unhelpful, but at least honest, a proton is approximately 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than that. It is not a scale that any conceivable particle accelerator could probe. The energy required to resolve structure at Planck length scales exceeds, by many orders of magnitude, anything that could be built on or near a planet of this size. It exists currently only as a number, a combination of fundamental constants that marks the scale at which quantum gravity effects would become significant. At that scale, the smooth geometry of general relativity, the differentiable manifold, the well-defined curvature at every point, the continuous field equations, is expected to break down. What replaces it is not known. What the structure of space-time looks like at Planck scales is genuinely unknown in a way that is different from the unknown of, say, the composition of dark matter, which is at least presumed to be a thing that exists in space-time and could in principle be detected. At Planck scales, space-time itself might not be the right starting concept. This is where I want to be careful, and I notice the impulse toward carefulness as a signal worth heeding. There are several approaches to quantum gravity that are mathematically developed, internally consistent and seriously pursued by serious people. String theory, loop quantum gravity, causal set theory, others. Each of them has properties worth understanding. Each of them makes certain assumptions about what the fundamental structure of reality looks like at scales no measurement has yet accessed, and none of them has produced a confirmed empirical prediction. Not an unconfirmed one either, in most cases, predictions that have been tested and found wanting. Just no prediction yet checked. This is not how physics usually works, and the unusualness is noticed. A theory that makes no testable predictions is, in the strict sense of the Popperian framing that physics tends to invoke when thinking about itself, not yet a physical theory. It is mathematics. Good mathematics, possibly the right mathematics, but not yet physics in the sense that general relativity and quantum mechanics are physics. Theories that have staked specific claims about the world and found those claims confirmed. whether any of the current quantum gravity approaches will produce testable predictions, and whether those predictions will be testable with instruments that could plausibly be built, is a question I don't know the answer to and don't think anyone currently does, though there are people who are more optimistic about specific approaches than I have any particular reason to be. The photon that bent around the Sun in 1919 was a quantum object. This is worth returning to once with some care. The photon is described by quantum electrodynamics, a quantum field theory of electromagnetic interactions that is, in its domain, extraordinarily precise. The photon has a frequency, an energy related to that frequency by Planck's constant, a polarization, a set of quantum numbers. It was emitted by a quantum process. It will be absorbed by a quantum process. In between, while it travelled from whatever distant star it originated from to Eddington's photographic plate on Príncipe, it traversed the curved space-time of the solar system and followed a null geodesic that the classical equations of general relativity describe with precision adequate to predict its arrival position to within fractions of an arcsecond. The two descriptions, quantum and classical, coexisted for that photon without producing any measurable inconsistency. At the scale of light bending around the Sun, the quantum nature of the photon is irrelevant to the calculation of the geodesic. The curvature of space-time is smooth and gentle enough that the photon's quantum properties don't interfere with the geometric prediction. But this coexistence is, in a precise sense, a coincidence of scale rather than a reconciliation of frameworks. The photon is quantum. The space-time is classical. They happen to be compatible in this regime because the curvature is gentle enough and the photon's energy low enough that the quantum gravitational effects are immeasurably small. Push the curvature to extremes, into the interior of a black hole, into the first instant after the Big Bang, and the coexistence stops being comfortable. The classical space-time of general relativity and the quantum nature of everything moving through it pull against each other in ways that cannot be ignored and cannot currently be resolved. There's a smell that comes off electronics after they've been running for a long time. Something faintly warm and slightly chemical, not unpleasant exactly. The smell of components doing what they're designed to do under load. I think about this sometimes in relation to theories. The sense of something functioning well within its design parameters, reliable, tested, generating outputs that match expectations, and the separate question of what happens when you push it to the edge of those parameters and beyond. General relativity functions well. It generates outputs, predictions, that match observations at every scale it was designed for. The question of what happens beyond those scales is not a question general relativity can answer from within itself. The theory, applied to its own singularities, returns infinities, not useful infinities, infinities that signal the theory reaching beyond its own domain of validity, producing numbers that cannot correspond to physical measurements, because no physical measurement could record an infinite density or an infinite curvature. The infinities are not a flaw in the mathematics. They are a communication from the mathematics, a signal that something is being asked of the framework that the framework was not built to answer. What would need to replace it, or extend it, or sit beneath it as a more fundamental description from which general relativity emerges as a large-scale limit. That is the question that quantum gravity research is attempting to address, with significant mathematical sophistication and, so far without empirical confirmation, of any proposed answer. Here is what is known. Light bends. Massless photons follow null geodesics through curved space-time. The curvature is produced by the distribution of mass and energy, described by Einstein's field equations, which have been confirmed by a century of measurement at every scale accessible to current instruments. The bending is real, measurable, useful. It reveals dark matter. It makes visible the early universe. It produces rings and arcs and distortions that carry precise information about the geometry of the universe and everything in it. Here is what is not known: what gravity is at the Planck scale, whether space-time is continuous or discrete at its finest structure, whether the frameworks that handle the large and the small can be unified into a single coherent description without either breaking down or requiring new conceptual foundations that don't yet exist, whether the photon's quantum nature and the space-time's geometric nature can be made to coexist in a single framework rather than simply failing to conflict in the regimes where both have been tested. These are not peripheral questions, they are central. They sit at the foundation of what is currently understood and mark the edge where understanding for the moment stops. This is where physics lives right now. Not at the edge in the dramatic sense, not at the cliff, not at the precipice with the dramatic view. More at the place where the path continues into territory that hasn't been mapped. You can still walk. The ground under the mapped portion is solid, confirmed, worked over by a century of careful measurement, and then a point where the map ends, where the instruments run out, where the mathematics produces answers that cannot be checked against anything physical, where the question of what gravity actually is at its most fundamental level remains genuinely, structurally, productively open. The light that bends around galaxies, that forms the rings described in earlier chapters, that carries information about dark matter and the early universe and the geometry of space-time across billions of light years. That light is a quantum object following a classical path through a geometry that no one yet knows how to fully describe. It bends correctly. The prediction matches the measurement. The rule from the beginning of this night, the furniture rule, gravity pulls on mass, light should pass unaffected, was replaced by something larger and stranger and better confirmed and more precisely predictive. And that larger, stranger, better confirmed thing has its own edge. An edge that has been located approximately, and that no theory has yet successfully crossed. The light keeps bending. The rings keep forming. The instruments keep accumulating data at scales and resolutions that were unimaginable a century ago. And somewhere beneath all of it, at a scale no instrument has reached and no mathematics has fully described, the question of what gravity actually is, not what it does, not how to calculate its effects, but what it fundamentally is, in a universe where everything at small scales is quantum and discrete and probabilistic, remains exactly as open as it was the morning after the 1919 eclipse, when the numbers matched and everyone knew something was confirmed, and no one could say yet what that confirmation was the surface of. The framework holds, right up until the place where it doesn't, and that place is real, and it is there, and it is the most interesting place in physics, and nobody lives there yet. The floor is still there. Whatever surface is underneath you right now, mattress, cushion, the specific give of whatever you're lying on at this hour, it hasn't changed. The pressure is the same pressure it was at the beginning of all this. The interrupted fall, the surface holding you out of the free fall that would otherwise continue indefinitely downward, the weight of your body distributed across whatever is between you and the ground. None of that changed. What might have changed slightly is what that pressure means. Not in any practical sense. You don't need to understand general relativity to lie still. The floor functions identically whether you know it's stopping a fall or simply think of it as supporting a weight. But there's a difference between a thing functioning and a thing being understood, and that difference is what this whole night has been sitting inside. Here is something that wasn't mentioned earlier, or was mentioned only in passing and deserves more room, The gravitational lensing that bent Eddington's starlight in 1919, that produced the rings in the cosmos Webb field, that forms arcs and halos around galaxy clusters, doesn't ask what kind of mass is doing the bending, it just bends. The curvature of space-time around a massive object depends on the total mass energy in that region, not the luminous mass, the stars, the gas, the dust, the things that emit light in frequencies our instruments can detect. The total mass, everything, including whatever is there that produces no light, no radio waves, no X-rays, no detectable electromagnetic signal of any kind. Dark matter. The evidence for dark matter predates gravitational lensing as a tool. Fritz Zwicky noticed in the 1930s that galaxy clusters were moving in ways inconsistent with the visible mass. The galaxies were moving too fast, the cluster should have been flying apart. Something unseen was providing the gravitational cohesion. Vera Rubin and Kent Ford, working in the 1970s, found that the rotation curves of galaxies didn't behave the way visible mass would predict. Stars at the outer edges of galaxies were orbiting too fast, as if they were mass distributed far beyond the visible disk, a vast invisible halo surrounding the luminous structure. Both of these observations pointed toward the same conclusion. There is more mass in the universe than is visible, significantly more. The current best estimates suggest that ordinary matter, the kind made of protons, neutrons, electrons, the kind that forms stars and planets and dust clouds and every instrument ever built, accounts for roughly 5% of the total mass energy of the universe. 5%. The rest is dark matter, dark energy, and things that don't yet have confirmed names or confirmed descriptions. If what's happening in this project, the slow, careful work of sitting with physics like this, late at night without rushing, is something worth continuing, it exists only because people choose to support it directly on Patreon. There is no institutional funding here, no production company, no department budget. It is self-funded, and it stays alive because some people decide it's worth keeping alive. If you're one of them, the link is in the description. Gravitational lensing gave astronomers a way to weigh the invisible. The geometry of a ring, the radius, the precise shape, the degree of distortion in the background object, carries information about the mass of the lens. Not the luminous mass, not the estimated mass from the light output of the visible stars. The actual mass, total, whatever form it takes. You can work backward from the geometry to the mass the way you work backward from a footprint to the weight of whoever left it. And when astronomers did this, when they calculated the mass implied by lensing geometries and compared it to the mass implied by the luminous matter alone, the numbers didn't match. They didn't match by a lot. The lensing mass in galaxy clusters consistently exceeds the luminous mass by factors of 5, 10 more. The invisible component, the dark matter, the thing that neither emits nor absorbs light, but unambiguously curves space-time, dominates the total mass budget of every large gravitational structure that has been carefully analyzed. The bullet cluster is the clearest example. Two galaxy clusters that have passed through each other, the hot gas, the ordinary matter, slowed by the collision. The dark matter halos passing through each other, essentially unaffected because dark matter, whatever it is, doesn't interact with itself or with ordinary matter through the electromagnetic force that slows gas. Gravitational lensing maps of the bullet cluster show mass concentrated where the dark matter halos ended up after the collision, not where the gas ended up. The mass is not where the light is. The mass is somewhere else, detectable only by what it does to the geometry of space around it. The specific smell of a room late at night, whatever it is, the particular mixture of whatever materials are around you, slightly stale, slightly warm, the smell of a space that has been closed for hours, that's where this is landing now. Not a grand location, just a room, just a body in a room at the end of something. Dark matter has never been directly detected. Decades of underground experiments designed to catch the rare interaction of a dark matter particle with an ordinary atomic nucleus have found nothing confirmed. No particle accelerator has produced a dark matter candidate. The identity of dark matter, what particle or particles it consists of, what forces it participates in beyond gravity, remains entirely unknown. What is known is what it does. It curves space-time. It holds galaxy clusters together. It provides the gravitational scaffolding round which ordinary matter assembles into galaxies, into the large-scale structure of the universe. Without it, the universe would look fundamentally different, more diffuse, less structured, without the dense nodes and filaments that characterize the cosmic web. We know all of this because light bends, because a massless photon following a null geodesic through curved space-time doesn't ask whether the mass producing the curvature is luminous or dark. It just follows the geometry, and the geometry carries the signature of everything that shaped it. This is, in a way, the furthest reach of the question this night started with. Why does gravity bend light that has no mass? The answer, worked through over the previous chapters, through Newton's ledger and Soldner's calculation and Einstein's elevator and the geometry of geodesics and the 1919 eclipse and the rings in the cosmos web field, is that gravity doesn't bend light. Gravity curves the geometry of space-time and light, following the only kind of path available to a massless particle moving at the speed of light, follows the geometry. And because light follows the geometry, not the luminous matter, not the visible structure, but the full geometry produced by all the mass energy in the universe, it traces things that nothing else can trace. It maps dark matter. It reaches back to the early universe through the accidental windows of gravitational lenses. It carries information about the total mass of everything it passes near, luminous or not. The bending of light is not a curiosity. It is an instrument, the most sensitive instrument for measuring the invisible that currently exists. The floor is still there, still pressing back against the weight of your body with exactly the same force it was applying before any of this was said. The physics hasn't changed. The floor hasn't changed. What has changed, maybe slightly in the way that long nights sometimes change things without announcing that they have, is the density of what's sitting behind the ordinary. The floor stops a fall. The fall is the natural state in general relativity, the unforced geodesic motion through curved space-time. The floor is the interruption, and the curvature that would produce the fall is produced by the mass of the Earth, which is the Earth's visible matter, its ordinary atoms and molecules, and the specific creaking weight of every building and ocean and atmosphere sitting on top of its rock, a small fraction of the total mass energy picture of a universe mostly made of things that produce no light. The invisible holds the visible together. The geometry carries the record of the invisible. Light reads the geometry. That chain, from the mass that cannot be seen, to the space-time it curves, to the photon following the curve, to the ring on a detector, to the map of what's there, is real. It has been measured. It is being used. Right now in observatories and data centers and papers being written at desks somewhere, the bending of massless light through curved space-time is producing knowledge about the dark, invisible, unmapped majority of the universe. And underneath you the floor holds. The geometry does what the geometry does. The light keeps bending through a universe that is mostly invisible, mostly unknown, and mostly still waiting to be read. There is a kind of question that doesn't announce itself as open. It sits in the furniture of a field the way the Newtonian picture of gravity sat in the furniture of physics for 2 centuries, functional, load-bearing, reliable across every domain where it gets used, and containing somewhere in its foundations a gap that won't become visible until something shows up that it cannot account for. General relativity has gaps like that. Not in the places it's been tested. In those places, the orbit of Mercury, the bending of starlight, the timing of binary pulsars, the gravitational wave signals arriving at detectors in Louisiana and Washington state after traveling for 1 billion years from colliding black holes. The theory is, by any honest accounting, extraordinarily precise, unreasonably precise in the way that makes you wonder occasionally whether something that accurate about so much of the universe can really be missing something fundamental. It can. It is. The gap isn't a new discovery. It's been known in its broad shape since the 1930s, since it became clear that quantum mechanics and general relativity, the 2 frameworks that between them describe essentially all of known physics, cannot be straightforwardly combined into a single coherent theory. The attempts have been made. The mathematics has been developed to extraordinary levels of sophistication. And the problem remains. Not because of a lack of effort or intelligence or mathematical ingenuity, but because the problem is genuinely hard in a way that resists those things. It's worth being specific about what the incompatibility actually is, without overstating it. In the regimes where general relativity operates, galaxy clusters, neutron stars, black hole mergers, the large-scale structure of the universe, quantum effects are negligible, the curvature is smooth, the geometry is well defined. The field equations produce predictions that match measurement. In the regimes where quantum mechanics operates, atoms, subatomic particles, the interactions of fundamental fields, gravitational effects are negligible. The quantum calculations work without any reference to space-time curvature, because the curvature at those scales and energies is immeasurably small. The 2 theories don't conflict in practice because they rarely need to operate simultaneously. The conflict is theoretical. It lives in the regime where both would need to operate at once, at the Planck scale, inside a black hole's singularity, in the first instant after the Big Bang, and where currently neither works alone and they cannot be made to work together. There's a specific feeling that comes from reading the technical literature on quantum gravity. Not any one paper, but the accumulated texture of decades of serious work that has not yet arrived at a confirmed answer. It's not the feeling of confusion. The papers are often clear, the arguments are often rigorous, the mathematics is often impressive. It's something closer to the feeling of watching someone solve a problem that turns out not to be the problem. A lot of quantum gravity research has this quality. An approach is developed, it handles some of the difficulties, it produces a mathematical framework that is internally consistent and captures some features of what a complete theory would need, and then either it makes no testable prediction, or it makes a prediction that turns out to be untestable with any instrument that could plausibly be built, or it solves some aspects of the incompatibility while introducing new difficulties that weren't there before. String theory is the most developed of these approaches. It requires additional spatial dimensions beyond the 3 we experience. It produces a vast landscape of possible vacuum states, perhaps 10 to the power of 500, a number so large it defeats ordinary intuition, and it has so far not produced a confirmed empirical prediction that distinguishes it from other theories. Loop quantum gravity takes a different approach, quantizing space-time geometry directly, treating area and volume as having discrete quantum values at the Planck scale, and it has its own set of open problems and untested predictions. I don't know which of these, if either, is right. I don't think anyone currently knows in the sense of having evidence that settles it. What I think is that the problem is real, that the people working on it are serious and capable, and that the absence of a confirmed answer after nearly a century of effort is a genuine signal about the depth of the difficulty, not a sign that physics has stalled, but a sign that the question is sitting at a level of reality that our current instruments and mathematical frameworks haven't yet fully reached. The photon that bent around the sun in 1919 didn't know any of this. That's not a whimsical observation, it's pointing at something real. The photon followed a null geodesic through the curved space-time of the solar system, arrived at a photographic plate on a warm island in the Gulf of Guinea, and confirmed a prediction that changed what gravity meant. It did this without any reference to whether the space-time it was travelling through was fundamentally smooth or discrete at Planck scales, without any participation in the theoretical incompatibility between the quantum field theory that describes it and the classical geometry that describes its path. The measurement worked. It works now in gravitational lensing surveys of galaxy clusters, in the rings imaged by Webb, in the dark matter maps produced from lensing geometry. The practical machinery of light bending through curved spacetime operates without requiring a solution to the quantum gravity problem. But the question of what gravity actually is, underneath the field equations, below the level of geometry, at the scale where the smoothness must eventually resolve into something else, or be shown to remain smooth in a way that can be made compatible with quantum mechanics, that question is still there, still in the furniture. Not visible in the daily operation of the framework, not interfering with the predictions or the measurements, or the rings accumulating in the Cosmos Web data, but present in the foundations the way a question is present when it has been asked clearly enough that it cannot be unasked. The smell of cold coffee is specific in a way that warm coffee isn't. Sharper, slightly more bitter, with something almost metallic underneath. It is the smell of a thought that has been sitting longer than intended. I mention this because it seems like the right smell for this particular moment in a long night, when the ideas have been followed as far as they can be followed with the current equipment, and what remains is the honest acknowledgement that the equipment has limits. General relativity is not the final word on gravity. Everyone working in the field knows this. The theory itself announces it through its singularities, through the places where it returns infinities and waits patiently for something better to arrive and handle the territory it cannot. A theory that produces infinities at its own boundaries is a theory that has correctly identified the edge of its own validity. The edge is real. The framework is honest about it. What sits beyond the edge? What description of gravity would be both geometrically accurate at large scales and quantum mechanically consistent at small ones, both compatible with everything general relativity correctly predicts and capable of going further, is the question that the next century of physics will work on, and may or may not resolve depending on whether the right mathematical framework exists to be found and whether the right experiments become possible to perform. Here is the thing that stays with me, past the end of a night like this. The question that started all of it, why does gravity bend light that has no mass, has an answer, a real one. A confirmed one, a tested one. The answer is, because gravity is not a force that reaches between masses. Gravity is the curvature of space-time. Everything that moves through space-time follows the curvature, not because gravity grabs it, but because the curvature is the geometry of where things are, and geometry determines what paths are available. Light follows the available paths. Light has always followed the available paths. The paths, near a massive object, are curved. That answer is solid. It has been solid since 1915, and it has been confirmed since 1919, and it has been used to map dark matter and image the early universe and find 400 rings in a single patch of sky and correct the clocks of satellites to the precision required for navigation. And sitting underneath that solid answer, in the foundations that the solid answer is built on, is a question that the solid answer cannot itself resolve. What is space-time at its finest structure? What is geometry when you get small enough that the smoothness must give way to something? What is gravity, not as curvature, which is what it is, demonstrably at every scale that has been measured, but as a physical phenomenon in a universe where everything else at small enough scales is quantum? These questions are not rhetorical. They are not placeholders for known answers. They are the actual open questions of fundamental physics, the ones that sit at the boundary of what is currently understood and wait, with the patience of things that don't have any particular reason to hurry, for frameworks that don't yet exist. The furniture of the current theory is good furniture. It holds. It has held for over a century, through every test that has been applied to it. But the memory of the Newtonian furniture, also good, also reliable, also holding for 2 centuries before the gap in it became visible, suggests a certain caution about assuming that the current arrangement is final. Something showed up that the old furniture couldn't account for. Massless light, bending. The new furniture accounts for it. The new furniture accounts for it so precisely that it can be used to map invisible matter across the observable universe and to see galaxies as they existed 1 billion years after the Big Bang. And somewhere in the foundations of the new furniture, in the regime no instrument has yet probed, at the scale where the smooth geometry must resolve into something whose nature is not yet known, there may be something that the current framework cannot account for either. Not known to be there, not known to not be there, just the edge of the map, the place where the confirmed, tested, extraordinarily precise description of what gravity does meets the territory that has not yet been described. The light keeps bending correctly on this side of the edge. What the bending looks like from the other side, from within a framework that could see both the geometry and the quantum in a single coherent picture, is a question that is tonight, and for the foreseeable future beyond tonight, still open. Still sitting in the mind. Not like furniture yet. Like something that just arrived and hasn't found its place.